All right, let's start. So hello, everyone. Welcome to episode 74 of Warsaw Quantum Computing Group meetups. And today we have pleasure to host our great speaker, Dr. Emil Żak from BAIT. It's a Polish startup working in quantum technologies domain, but not only quantum. And Emil will give a talk about simulating high accuracy nuclear motion Hamiltonians in discrete variable representation using Walsh-Hadamard QROM with fault-tolerant quantum computers. Before we start, just a few announcements. So as you can see, this meeting is recorded, so we are planning to upload the video to our YouTube channel. And we've agreed with Emil that there will be a Q&A session at the end. So if you have any questions, you can post your questions on the chat, or you can keep it until the end, and then there will be a dedicated Q&A session when you can raise your hand and ask a question. Before we start, we would also like to thank our strategic partners for supporting us: Sonovero R&D, Quantum.io, Onyx, FinQubit, Cogit, AIQ Lab, and our honorary partners for helping us advertising the event. I will stop sharing my slides now. So Emil, if you are ready, so the Zoom is yours. And first of all, thank you again for accepting our invitation. It's a pleasure to have you here, and we are looking forward to your talk.
Thank you very much. Can you hear me okay?
Yes, I can hear you.
Great. Okay. Can you see the slides?
I can see it.
Okay, thank you. Great, so I can start. Hi, everyone. And first of all, big thanks to Pavel for inviting me and giving me this chance to talk to you today. It's a great pleasure to be here. And for the next 45 minutes or so, hopefully a bit longer than that, I'd like to say a few words about fault-tolerant quantum simulations of Hamiltonians. And my particular interest is in nuclear motion Hamiltonians. I'm going to explain along the way what it means. So to start, what is BAIT and where I come from? I'm a physicist at BAIT, and BAIT has been founded quite a few years ago already in 2017 by Wojtek Urkot, Witek Jarnicki, and Paulina Mazurek, three ex-Googlers. Unfortunately, Wojtek passed away some time ago, but we carry on, carry the flame, and we're moving on to new adventures. So today, if I were to describe what we do in one sentence, that would be, I would say that we develop molecular modeling tools to support drug discovery mainly, but also we focus on physics simulations as such. And for that purpose, we use both classical computers and quantum computers. We've got two offices in Canada and Poland, Krakow, and with around 20 employees in total. I think, represent a mixture of mathematicians, computer scientists, physicists, chemists, and drug discovery experts. So it's quite a zoo. And the plan for today is to talk about one aspect of our R&D. And here in this slide, you can see some bird's eye view of our R&D currently. One area that we focus on is quantum algorithms for chemistry. This nuclear motion theory that I'm talking today falls within this batch. Within this algorithms for chemistry, we specifically care about hybrid computing. So how to make the classical architecture communicate with quantum efficiently. We model vibronic spectra. We do some theoretical analysis of quantum advantage. We seek for this quantum advantage, and we simulate different phenomena like attosecond physics. But this is mostly algorithm design. We also develop methods for, let's say, today use. So mostly quantum chemistry for drug discovery. molecular docking, and some beginning to end pipelines for drug discovery. So here in the middle, you can see some of our partners, and with their help, we're building our tools. And some of these tools has been around for a while, like our QUBO solver, but some are new, and some sort of new branch is that we focus on molecular dynamics simulations with high performance architectures like wafer-scale engines or multi-GPUs. And we try to train machine learning force fields for that. So this is an overview of our research. And what is the context for today? Well, the pipeline that I'm going to go through, I think it could be summarized with this simple workflow, let's say. That we start with a molecule of interest. This might be a molecule that comes from our partner, somebody that knows what is important and it is unsolved, for instance. And we digitize this molecule and encode it into a matrix, the Hamiltonian matrix. And these matrices are usually too large to be handled by classical computers. So quantum computers hold some promise for being useful here. So if you have your digitized molecule encoded in matrix, what we do next, we design an algorithm that will help us learn something about the molecule. For instance, calculate the energy levels of this molecule. And then we pass it on to existing quantum computers, also with partners, and see what happens. Alternatively, we write down the algorithm and wait until the hardware catches up. So we locate ourselves somewhere in the middle. So in algorithm design. So this is the context, and the specific problem I'd like to talk about today is I'd like to solve the Schrödinger equation for a specific type of systems and motions. So the systems are molecules, gas phase molecules, and the motions are rotations and vibrations of these molecules. And so you might write down the Schrödinger equation for this scenario, let's say. So it's given here in the bottom. And we have two components, as always in the Schrödinger equation, the kinetic energy operator, K, and the potential energy surface, V. So if we solve this eigenvalue problem and find the eigenvalues, which are energy levels in this case, you can say that you've solved at least partially the Schrödinger equation. And this kinetic energy operator is basically the kinetic energy for the atoms, for the nuclei, how they move. So, it might be decomposed into different components, let's say. So there's the vibrational motion, how the molecule vibrates, but there are also other effects, like the Coriolis coupling. You might know it from Earth, the Coriolis force. And the rotational motion. So the kinetic energy operator might be pretty complex. I'm going to show it in a moment. And the potential energy surface, V, it's usually expanded in a form of, we call multimode expansion. It's not particularly Taylor expansion. It's a specific type of expansion. And the potential energy surface depends on all internal degrees of freedom in the molecule. So bond distances, bond lengths, bond angles, and dihedral angles. So it's a function of almost all let's say atom positions in the molecule. So once you have this and you want to solve this, that's quite a challenge. And if you do this, if you just get to solve this equation for large enough molecules, you create impact on different fields. So there are fields that await solutions to this class of Schrödinger equation, because you can learn something from first principles, and there's no experiment, there's no fitting, and later on you can verify against experiments. But first you obtain something from first principles, and you trust that's accurate, because quantum mechanics has been tested quite well. So if you let's say solve the Schrödinger equation with a quantum computer, you need a set of algorithms or set of instructions to be passed on it and feed it into the quantum computer. And this solution, let's say, gives you information about different properties of the molecules, and then you just map it to applications like novel materials, multi-junctions, how to design new batteries, for instance, how to predict spectra of molecules in astrophysics, or how to model chemical reactions. So this is what we specifically do. We focus on biochemistry, and here these solutions really matter. And if you can do this with a shorter algorithm, let's say shorter circuit, we say, with fewer qubits, you get a couple of advantages. The first one is that the time to solution might be shorter on a quantum computer, let alone the classical computer, which might be totally out of question. So I'm talking about cases where the classical computer doesn't handle it at all. You might spend less money because of that. Yeah? The quantum computing time is money, essentially. And also because hardware grows at a given rate. Yeah? So the number of qubits grows at some rate over the years. If you shrink the number of qubits, or we say if you shrink the quantum volume for the computation, this computation might become available sooner. So this impact might come in sooner. So it's quite worthwhile to design algorithms that are shorter in a way, yeah, so that use smaller quantum volume. And one specific example I'd like to show you is it's very recent. I just found it in some news feed. Is that it's from February this year. Scientists discovered a molecule in space that hints at origin of life, and it's a molecule with sulfur in it. And in order to detect it, they had to use spectroscopy and the JWST telescope, I think. And in order to know what's coming from this distant object, you need to have a reference spectrum. And the reference spectrum can be either measured in the lab. Sometimes it's hard and tedious, there are systematic errors, or you can calculate it. And then you are sort of confident that you have uniform error control, etc. So this is one piece of motivation. Accurate reference spectra for molecules could help, let's say, still dig out and identify new molecules in spectra that had been measured before. So it's quite exciting, and you might actually hint on discovering life. Another example is, especially when you have the biochemistry context, there's a lot of water in it. Yeah, so proteins are surrounded by water, and they usually form some hydrogen bonds. These water molecules, they form networks. And in order to understand these mechanisms accurately, like very accurate, and this is the end goal of quantum computing, not to resort to approximations, but at least to have error control. So when you want to have it very accurate, you need to solve the row vibrational or vibrational Schrödinger equation for water clusters, which is notoriously hard. This is the hardest problem for vibrational Schrödinger equation, when you have a very floppy system that can move around a lot. So we say the calculations often don't converge. And in order, if you compute these properties of these water clusters, you can learn a lot about the processes of drug protein docking, for instance, or other processes in human cells. So if I were to summarize the impact, drug discovery, proton transfer, chemical reaction modeling, catalyst design, artificial photosynthesis, etc. In astrophysics, naturally, so these reference spectra for exoplanets, biochemistry, and also some high quality data for machine learning models. So you can try to train your models on accurate, trustworthy reference data. So now I'd like to say a few words about the computational model that we adopted. So for solving exactly this problem that I stated. And here, a big shout out to two of my fabulous colleagues, Michał Szczepanik and Akush Nagy, who developed most of this computational model. And they did a remarkable job here, as I'm going to show you. So coming back to the Hamiltonian, you remember we've had the kinetic energy operator and the potential energy surface. And let's say that we have a molecule that has A atoms, okay? And the dimensionality of the problem that we are going to solve is going to be D. It's 3A minus 6. So this is the number of vibrational degrees of freedom in the molecule. And here you can see an example of SO2 molecule, SO2. And SO2 has 3 atoms. So 3 times 3 minus 6 is 3. So there are 3 vibrational degrees of freedom here. And here's an example potential energy surface for SO2. But it's impossible to plot a 3-dimensional surface on a flat screen. So these are only 2 coordinates, R1 and R2, R1 and R2, which are bond lengths for a fixed angle theta, okay? So this is how the PES, we say, potential energy surface might look like. And this is represented by this function. So going a little bit deeper, if you write down the kinetic energy operator exactly from first principles as using quantum mechanical canonical quantization rules, you might write it down as such a sum with Pi corresponding to the momentum operators for the ith degree of freedom, and Gij of Q is some matrix that couples different motions. So Q are internal degrees of freedom, bond lengths, bond angles, okay? And there's 3A minus 3 of those because there's 3A minus 6 vibrations plus 3 rotations. As you can see here, rotations, and there are also vibrations that have this Coriolis coupling in it. And if you were to write down the vibrational part, this would be like this. And there is already D, so 3A minus 6. There's Coriolis part, which has the momentum operators P, but also the angular momentum operators for the rotation of the molecule. So there's a coupling between rotations and vibrations. And there's also the rotational part, which depends only on the angular momentum operators and inverse moment of inertia tensor. So this is exact, and all motion couplings are included. And on the other end, our model concerns general potential energy surfaces. So we don't assume anything about the PES. It's not Taylor expansion. It's not normal modes. It might be neural network. And this is, in fact, where the most accurate potentials come from. And neural networks are by no means separable into sum of products. They are almost black box. So this is our model. And now, how to represent the Schrödinger equation once we wrote it down, right? once we wrote the Hamiltonian? Well, you might want to choose a basis set in which you represent your Schrödinger equation. And one popular way is to use the variational approach, so variational representation. So in the variational approach, what you do is you take the Hamiltonian, so k plus v, and the whole Schrödinger equation, and expand this wave function in a finite basis. So we say that psi is some linear combination of basis functions, and we call this variational basis representation, or VBR. And there's n of those functions. So once you do that, you convert this notably differential equation into a matrix equation. It's a matrix eigenvalue equation where we have the corresponding matrices for operators. And there's also the overlap matrix because the basis might be not orthogonal. And what are these basis functions? Well, we adopted, let's say, a fairly standard model where the rho vibrational basis, it's written here, it's a sum of products of vibrational basis functions and rotational basis functions. And the rotational basis functions are so-called Wigner D matrices, or they are solutions to the symmetric top model. And the vibrational basis functions are just sums of products of vibrational wave functions for individual coordinates. Yes, so this is a tensor product of D different basis sets. This hints on the complexity of the problem. What are these matrix elements, V? Well, if you do the calculation, so you expand the wave function in a basis and project it onto the same basis, these elements are basically matrix elements of the potential energy surface in our basis. And this is an integral. Yeah, so you integrate over all the components, all the dimensions that the PES has, so the D dimensions. So it's a multi-dimensional integral. Once you do that, so you calculate your matrices, so K matrix, V matrix, and S matrix. Once you have this, this is just an algebraic problem or numerical problem, and it can be visualized like this. Yeah? So H matrix, so K plus V, or U, it's a unitary matrix of eigenvectors, is S times U times E. Yeah? So this is the standard way for formulating the eigenvalue problem in matrix form. And if you were to use classical solvers, the computational complexity scaling depends on the sparsity of your matrix. If your matrix is dense, you need to use direct eigensolvers, or if you want to get many eigenvalues, and the complexity is n cubed, yeah, where n is the total number of basis functions. On the other end, if you use iterative eigensolvers, it's more closer to the O of n, so linear scaling, but there's a trade-off. Yeah? You either have a sparse matrix or you care about very few eigenvalues. So once you solve this equation, what you get are energy levels. There are vibrational and rotational energy levels. We basically say there are rho vibrational energy levels. And this is what we want to calculate. This is what this algorithm will be about. So here's an example for a diatomic molecule, like I know CO molecule. On the x-axis, there is the distance between the atoms. The y-axis are the energy levels. And it's on top of the potential energy surface, which is one-dimensional in this simple case. And once you get the energy levels, you might predict the spectrum, and then you might send it off to comparison with measurement from distant exoplanets. So this is more or less the way you might go. One thing that might be relevant here is that if you recall this this vibrational basis that we used to represent the Schrödinger equation with.
Yep, it seems there are some technical problems. Emil, we cannot hear you now. We cannot see your screen. Okay.
So I'm going to share my screen now.
All right.
Is it better now?
Yes, it's better.
Okay. So I think, despite of what I said, this is not critical to understanding the next part, unless I've been cut off 5 minutes ago. But I hope the break was very, very short. So the important message here is that once you choose your molecule and you choose your basis set, you know what's more or less what's the complexity of your problem. So if you choose, let's say, water molecule with 3 atoms, and you want to calculate energy levels, you might need around 1 kilobyte of RAM. Because imagine you use 10 basis functions per dimension, and you have 3 dimensions. So it's 10 to the power of 3, roughly in the kilobyte range. 4 atoms, it's roughly 1 megabyte, because 4 atoms is 6 degrees of freedom internal. 5 atoms is already around 1 gigabyte. It might be around 3 weeks of runtime. 7 atoms, 1 petabyte, and 25 years of runtime. And 9 atoms might be exabytes and zillions of years. Of course, I'm exaggerating a little bit because there are approximations you can make, and there are some efficient classical methods to get approximate spectra. But if you were to solve the exact variational problem, this would be the scaling. So the scaling goes up exponentially. So we say these calculations succumb to the curse of dimensionality. So for comparison, I think Encyclopedia Britannica weighs around 4.3 gigabytes. So we need way more than that to describe these molecules. And so once we know about the model and the variational representation, there are some advantages coming from reframing the problem into a particular basis where the Schrödinger equation is particularly simple. And this basis is called discrete variable representation. So the way you arrive at the discrete variable representation, or we say DVR, is that you take these matrix elements that I showed you before for the PES, for the potential, which are represented as an integral, and you approximate this integral with quadratures. So you approximate the integral with a sum. And once you do that, you might convert this matrix element into an element of product of 3 matrices. One matrix is exactly composed of the values of the potential at a given grid. And the T matrices, here and here, are just evaluations of the basis functions at these specific grid points, also weighed by the quadrature weights, because every quadrature that approximates an integral has some weight coefficients. So once you define your T as such, and P is just a polynomial, because usually we use polynomial bases, your matrix that was used to represent the potential in VBR now decomposes into a product of 3 matrices where the middle one is diagonal. And T is basically the transition between the let's say, VBR and DVR basis. So it's a basis change. And I allowed myself to plot such T matrix for n equal 128 for a given choice of quadrature. It's called Gauss-Hermite quadrature. So more or less, this is how this matrix looks like, and it's unitary. So once you do that, you can convert your Schrödinger equation by replacing the VBR with this product. And now you can do a little bit of algebra. For example, multiply from the left by T, the inverse of T transpose. So you remove T transpose. You remove T transpose here. And the T transpose inverse lands here. So this is here. And you might define a new basis, which is defined by T times U, which is Z. And this simple step gives you the Schrödinger equation in DVR. And what's quite remarkable here is that the potential, the PES part is diagonal. So one feature of DVR is that the PES is a diagonal matrix. There are some advantages of that because it's a many-body potential, it's complex, and you don't need to evaluate these integrals, the multi-dimensional integrals. And the kinetic energy part is usually much, much simpler. It's lower body count. As the couplings are not as critical as in the PES. So schematically, what the DVR does, it converts your PES, that might look like this, the matrix, through these DVR bases into a diagonal form. And now the task is basically to produce a quantum algorithm for that. So this is what we did. I'm not going to talk about much about that. I'm going to reference you to our paper. But the general concept is that these DVR transformations, they rely on orthogonal polynomials, which they obey the three-step recurrence relations. And as Hermite polynomials, Jacobi polynomials, Legendre polynomials, they are constructed recursively. And you can exploit that and construct this matrix, basically encode in a quantum computer such a matrix quite efficiently through the circuit I showed here, but I'm not going to go into the details of this circuit. It's not critical here. So I can feed you the paper. The punchline is that, well, once you found a way to encode the DVR transformation on your quantum computer, then extension to more dimensions is straightforward. So here I was only showing the DVR transformation for one dimension, for one coordinate. Yeah, and our problem is d-dimensional. And if you use a direct product basis, as we do, the multi-dimensional DVR transformation is just a tensor product of individual transformations. And in a quantum circuit, if it's a tensor product, the depth doesn't grow compared to a single component. It can be done on separate qubit registers. You just need to multiply the qubit registers. So this is quite useful here. So it's cheap. We might say that we've washed away this problem. And now the essence. What time do I have? Okay. The essence is block encoding. And block encoding is essentially a way of embedding the Hamiltonian matrix that we constructed, I showed you before, into a unitary circuit. And so we've got our Hamiltonian, and we've got a bigger unitary circuit, and we want this Hamiltonian to be embedded in the top left corner. So I'm not going to talk much about this, but this is the idea. And there are circuits for doing this efficiently. And we designed one such circuit. And in order to do that, we first have to encode our problem into qubits. So you might remember the vibrational basis functions, V sub c. So for every c, this is the coordinate, we have a set of basis functions of a ladder of energy levels of harmonic oscillator, let's say, that we use to represent the solution in this dimension. And basically what you can do is you can represent this basis function on number of qubits, which are in the tensor product relation, and eta c is essentially a logarithm of basis functions along one of the coordinates. And same with the rotational basis function. So it's a straightforward one hot, we say, encoding. So once you encoded your basis into qubits, what you can do, you can start approaching the block encoding algorithm. And the most straightforward way to do that is through something called linear combination of unitaries. And so for the record, to recall, we started with the kinetic energy operator, or we say KEO, which was the sum, you remember, of momentum operators. We converted it into the DVR representation through these T matrices. There's still the sum, but now these are matrices, and there are matrices for the momentum operators, the momentum matrices for the G matrix from here, and there are these T matrices that we know how to encode efficiently, and because there are these tensor products of single-dimensional DVR transformations. So the unitary circuit for block encoding this KDVR, so putting it here in the top left corner of the big matrix, is denoted with B of K DVR, and it's given by such a train of transformations. And you might recall in LCU, we say, in linear combination of unitaries, you have two types of circuits. One is the state preparation, and the other is the selection of unitaries. So here is the same. G is some sort of state preparation. And there in the middle, there are some selections of unitaries. And these operators, UP, UG, they look like that. So they are, as I said, they are selection operators, so they are conditioned on some registers. And once this qubit takes this value, you basically execute block encoding of individual operator, like the momentum operator here. So UPs are essentially LCU select operations that allow to encode this linear combination of unitaries. So it's we say it's a sum of block encodings. And the circuit looks like this. So there's G, state preparation, which encodes the coefficients of this linear combination. There's T matrix, which is easy. And there's a couple of selection operators, which basically represent this UP, UP prime, and UG. So in order to get this, you need to also produce block encodings for individual momentum operators and G matrices. And so if you wanted to complete the Hamiltonian, because this was only an example for the KEO, you can complete it with the PES by just adding just one extra control register with conditional execution of the potential, and this is a complete UG operator that encodes the Hamiltonian in DVR. So now we focus on these B of V, B of P, B of G. So block encoding, but of the individual matrix representations of momentum, G matrix, and the PES. And if we focus on the PES, so you remember this is a diagonal matrix. So if it's a diagonal matrix, I think we can do it cheaper than the generic methods for block encoding. And so we came about a method we called roughly, and it's a working name, canonical operator method, where in order to block encode a diagonal matrix, you need QROM that loads the values of this matrix. So this is QROM. So OD acting on some address register returns the value on D qubits. And also some other type of operator, we call it A operator, canonical opposition operator, that if it acts on a qubit register that represents Y, it returns the value Y times the same register. So now if you combine these two operators in such a string, OD, A, tensor, identity, OD, dagger, and you apply these definitions step by step. So first you act with QROM, then you act with A on the second register, and then we say uncompute QROM. You end up exactly block encoding of a diagonal matrix, for instance, DVR. So the price you pay for this canonical position operator is very low. It can be expressed with poly Z operators because it's diagonal. So it's cheap. There's a cost for that. And the cost depends on the number of qubits, but it's linear in the number of qubits. So it's basically negligible. The big part is QROM. So the cost of QROM in normal setup costs roughly square root of the capital N. So of the total size of the DVR matrix, which might be huge. And you only need 2 calls to the QROMs and 1 call to this position-like operator. So it's a method that might be useful in conjunction with specific QROMs. So now, if you want to carry on with the resource estimation and you recall these UP and UG operators, the UG operator required block encoding of the G matrix, and this is diagonal, in DVR. Every local operator is diagonal in DVR. PES is diagonal, and G is also diagonal because it's a function of coordinates alone. So we can use the same method as for the PES. And for the momentum operators, we applied a trick that you can decompose the momentum operator in DVR, which is non-diagonal, it's by no means diagonal, and do spectral decomposition. And this guarantees you optimal block encoding constant. There are benefits from that. So now when you put all this together, so you remember the circuit looks like that. This is basically the representation of the circuit. If you sum up all the costs along the way, so the cost of block encoding, this is expressible by the cost of QROM, or basically a cost of diagonal unitary synthesis. You end up, and you do some approximations, some maths, but you just leave the leading terms. You might assess the T-gate cost for these individual components in your block encoding circuit. So you might notice that the T cost for these UP and UG operators is essentially expressible by a lowercase n, which is the number of basis functions per dimension. Okay, so it's very very favorable scaling. Our total basis size is a small n to the power of d, and d might be large. The tricky part is V, so how to block encode the potential energy surface, because this scales with normal QROM. We can call it select swap QROM. from Law et al. It scales exponentially with the number of atoms. So it's lowercase n, roughly to the power square root of 1/2 of d. So d is the dimensionality, or 3a minus 6, where a is the number of atoms, you remember. You can also make some reductions, but there is little hope. So what we did, we designed a new QROM, which reduces this nasty complexity by a significant factor alpha. So this complexity is, we might say it's still exponential as every complexity here, but the exponent is much, much lower. So as if you had fewer atoms, like half the number of atoms, maybe quarter number of atoms. And this is the Walsh-Hadamard QROM. And in a nutshell, what this Walsh-Hadamard QROM is about, if you recall the standard QROM, which is a function that encodes an address register on n qubits into value register on d qubits, and it's a unitary, that encodes some function of x of the address register. So Walsh-Hadamard QROM essentially uses Walsh-Hadamard transform, which is like Fourier transform, but for pseudo-Boolean functions. So if you have a Boolean function, Fourier transform becomes Walsh-Hadamard. So it's a discrete combination of elements. And I'm not going to go into too much detail about the construction. It can be found in our paper, and I can send you that. But the way you approach it, you take your data. So you take your potential energy surface, which is just a function. It's a function of many arguments and you transform this function through Walsh-Hadamard. And once you do that, you truncate the tail of very, very small components. And then you might invert it. It's like Fourier transform. And if you invert it and you apply a appropriate circuit, you might encode compressed information about the function quite efficiently. So the intuition is that once you have your diagonal PES with more than 1 billion numbers, it's still hard for standard QROM to load it on a quantum computer because you need roughly the same number of operations. But with Walsh-Hadamard, you convert it into an approximate image, like here with Goofy. You have Goofy is the exact image. You convert it into inverse space in binary, and then truncate a little bit and convert back to the original representation. So with our choice of QROM, with this Walsh-Hadamard and appropriate truncation, what we observed is that our T-gate resources and qubit resources are reduced exponentially compared to existing techniques for QROM. And this is, I think, best visible in this table. So we took a number of molecules with given dimensionality, like methane, water, etc., etc., and then counted how many Toffoli gates we're going to need in order to encode a PES for this molecule. And what we found out is that this cost is always 2 to the power of n, where n is let's say it's a number of qubits, but the prefactor is much smaller than 1, as in select method for QROM, and sometimes it's smaller than 1/2, which is even smaller than the select swap QROM, which requires even exponentially more ancilla qubits. So our approach requires exponentially fewer ancilla qubits compared to select swap if you match the number of Toffoli gates. And there's quite favorable error scaling. This is also not a big problem. So with this advantage, we combine these pieces together. So the block encoding, the DVR, and and Walsh-Hadamard QROM, which performed quite promisingly on these molecules, and we tested it on a water molecule and did resource estimation. So we wrote down the Hamiltonian for the water molecule. So this is the exact kinetic energy operator in some coordinates. We took potential energy surface from high end, so it's a very accurate potential energy surface from Wang et al. And then we estimated what would be the T count, the number of qubits and number of Clifford gates that you need in order to block encode this Hamiltonian. And if you used standard LCU method, your scaling in T count would be like roughly n to the 6. On the other hand, if we use our DVR represented Hamiltonian with appropriate tricks, this reduces to n to 3 halves. Same with Cliffords, and same, and also the number of ancillas is, I don't know if it's an error or not, maybe not. But when you do the quantum volume, so when you multiply these numbers together, the DVR plus FBR, we call it costs roughly n cube, whereas LCU would cost roughly n to the power of 13 halves. Yeah, so that would be 6.5 ish. So the reduction is more than 3 powers. So it's a polynomial reduction, and we didn't use any Walsh-Hadamard QROM here. So it's just by the choice of DVR and the choice of the Hamiltonian block encoding. So we went a little bit further to show this better, and we counted the number of gates specifically for a given number of basis functions for given PES. So it's a real life example. And if you wanted to calculate the energy levels for water, you would need 2 times 10 to the power of 11 T gates with LCU. Whereas when you use the method that we presented, the reduction is between 5 and 6 orders of magnitude. It's sometimes unfair to compare only T count because you also care about the ancillas. So we also compared the fixed ancilla T count, so equal ancillas and how many T gates. And this is, again, 100,000 reduction in resources. So we thought, okay, let's benchmark this further. Does it work on larger molecules? And here it is. So first we took methane. And for methane, we already invoked our Walsh-Hadamard QROM because this is where advantage really starts kicking in. So if you compare the cost for block encoding the PES for methane, which is a 9-dimensional molecule, and it has 5 atoms, you might need around 1 billion gates with select swap. With Walsh-Hadamard, you might imagine, okay, but I need roughly the same number of gates. So where's the advantage? Well, the advantage is the number of ancillas. Select swap would require equal number of ancillas, whereas we need roughly 200 ancillas. So again, quantum volume is reduced 1 million times here. Again, we expanded and we moved to larger molecules. 30-dimensional molecule, which is classically intractable. And here are the resource estimates. So let's look at this select swap QROM select swap, okay, this line. And 6 times 10 to the power 48, like totally ridiculous number. And you can also reduce it by some tricks. We tried hard. We boiled it down to 10 to the power 18 in quantum volume. And then when you compare it with Walsh-Hadamard QROM, the reduced version, it's again 1 million times fewer gates times qubits. So the quantum volume is shrinked 1 million times ish. And what's quite remarkable is that the design of the algorithm assumes that as you progress in the rotational excitation of the molecule, the resources don't tend to be changing significantly. So this is important and classically hard, because in classical computation, the scaling with the rotational excitation is linear to quadratic. And here I'm going to show it to you. It's square root and it's additive. So here you can see some resource estimations for different values of the rotational excitation J0, J100, 200, 400. So J400 is highly excited state, and it costs roughly the same as totally rotational ground state. So it's a very favorable scaling in this respect, and it's also important. So once you have these estimates for block encoding, you might want to know what's the actual cost for learning about the energy levels. Because this is what you care after all, right? So you want to estimate the rotational vibrational energy levels, and for that purpose you use quantum phase estimation. Yes, and quantum phase estimation is a circuit that uses block encoding as part of it, and its total cost of the QP is proportional to the cost of block encoding. There's also this block encoding scaling constant that's important. So with these estimates, we count a number of T gates and qubits for different molecules, starting from methane, as you can see here, through 21-dimensional, 30-dimensional, 51-dimensional molecules. All these molecules are beyond classical reach. And it turns out that the number of qubits is in the low 200s. And the number of T gates is also within reasonable limit. If you follow electronic structure theory and what people do there with quantum algorithms, these are roughly the same numbers. So you could at least think about simulating these energy levels with our method, and probably it would be totally a formidable task and totally without perspective if you wanted to do it with, let's say, standard LCU, because it will be millions of times more gates and qubits. So an example is 50-few-dimensional molecule is dopamine. If you want to model dopamine, with our methods, you might need roughly 10^14 T gates and 240 qubits or 250 qubits. Okay, and the final straw, I would say, is to generalize it. And what's the general scaling for our method? So you might recall this table where we compared these different scalings. And I must say there's this disclaimer that the scaling depends on the coordinates you choose to represent your molecule. And if you choose something called the polyspherical coordinates, which is a popular choice, then you can give good and rigid scaling. And the scaling of our method is like that. It's quite a few terms. And the leading term, again, is this term coming from the potential energy surface. So it's 10 n to the power alpha d. And this alpha, in our case, was, as you remember maybe from the table, in the range 0.25 to 0.6 ish. So this is the scaling of the method. And now, how about we compare this scaling with the scaling of classical computing methods? So I divided the two and encapsulated it under the O of tilde notation. So we drop logarithmic terms so as to give a feeling. So if you compare the number of qubits to the number of, let's say, bits, in classical computing, our saving is exponential with the number of atoms, which is expected. This is what you expect from a quantum computer. Although select swap can break it. This is the issue. And the speed up is also I would say at least polynomial, or I call it super polynomial in some specific sense. So if you divide the number of T-gates by the number of flops you need for the computation, the classical computation will require this much more operations, which scales again exponentially. So it's an exponential speedup in this respect. And there's also J. Remember, this is the rotational excitation, and it enters as additive, not multiplicative. So it's a difference to classical algorithms. This is what we discovered, and it's quite promising because it's not only not linear, but it's quadratic speedup, but it's also additive instead of multiplicative. So on top of these, let's say, advantages, which are to be tested in real life, our true advantage is that we have controllable and high accuracy for the model and controllable precision for the energy levels. We can control it by the number of estimation register size in QPE. So the take-home message is that this is, to our knowledge, the first algorithm that addresses this high accuracy in nuclear motion Hamiltonians. And it's not narrowed to that. Any class of problems that falls within the same mathematics can be solved on these algorithms, of course. And if you apply existing techniques to our exact setting, you would require exponentially more quantum resources with system size. Of course, there are methods that can alleviate this unfavorable scaling on the classical end, but I'm comparing to generic ones. So the one of the last slides I want to show is the sort of location of our work within other works, and this graph might be helpful. So on the x-axis we have number of dimensions, so number of atoms in the molecule, and on the y-axis you have different levels of theory of increasing accuracy. So on the top you've got relativistic effects and non-Born Oppenheimer, we say, and our work locates let's say in accuracy above the other works because we address this exact kinetic energy operator and non-sum of products PESs, and also is somewhere in the range of 12, maybe 50, 60, 100 dimensions. Other quantum techniques for vibration motion use just lower quality methods. So they assume some specific forms for the Hamiltonian or sum of products. So they wouldn't be able to achieve the accuracy that's needed. And there are also classical methods. So this is where we locate, and naturally we aim at the region where the problems are intractable classically. So there's some division here with this rainbow line. That's on the left-hand side you have tractable. On the right-hand side, this is intractable. So a little bit. And this is basically the last thing, very short. A little bit of doodling and having fun with back of the envelope calculations. So you remember this quantum phase estimation, T-gate counts and ancillas. So we put it into a simple calculator and try to estimate how much time you would need if you run a 21-dimensional molecule like dimethyl sulfide on this frontier supercomputer, or I think it's El Capitan supercomputer, which is, let's say, an exascale, one of the fastest supercomputers in the world. You would need 7,000 years and petabytes of RAM, and with this quantum algorithm that runs on 1 megahertz fault-tolerant quantum computer, you might need roughly 3 months and 250 qubits. And dimethyl sulfide is important because it's biosignature molecule, and it's yet to be detected, I think, in space, unless it's been detected. And this brings me back to the recent news on discovery of some very, very similar molecule. So we came up with this work months before this has been published. And so there's some motivation to carry on. And again, dopamine, very important neurotransmitter, supercomputer, longer than the age of the universe, an exabyte of RAM, quantum computer with our algorithm 9 months, 300 qubits. Of course, there are classical methods that can improve this significantly, but I'm comparing to, let's say, generic variational methods. Okay, so I'm gonna only say that we developed and combined 3 methods, or 3. Yeah, in fact, there are 3 methods they work synergistically. One is a method for block encoding the Hamiltonians with exact kinetic operator and non-sum of product PESs through optimal partitioning, spectral decompositions, and this canonical operator method. Second was quantum DVR algorithm, and the third part was Walsh-Hadamard QROM. And we combine these, and as a result, we need exponentially fewer quantum resources than other techniques. It's a polynomial asymptotic speedup compared to classical techniques, but it's on top of this exponential memory saving. So this is the result of that. But there are also some issues with our approach that we need to resolve. And one is calculating and block encoding and encoding these high-dimensional PESs. But we have some ideas how to go around that. With that, I'll thank you for staying with me, and I'll be really happy to answer any questions you might have.
Great, fantastic, thank you. Thank you, Emil. All right, let's see if we have any questions. I can see one question on our chat. So this is a question from Bartek. What software hardware do you use to develop quantum algorithms and conduct research? Are those products accessible to hobbyists from a cost perspective?
Mm-hmm. So when it comes to hardware, we have several channels. One is through publicly available AWS services, for instance, or Microsoft Azure, and you can connect to IBM quantum computers, IonQ, Quantinuum, Quera, and many more. So we use all these pieces of hardware. We also have partners that, let's say, allow us to use their hardware, preferably. So the way you do it, you submit your circuit to computer, and you return in a couple of hours. You get what the computer calculated, so a string of zeros and ones. Yes, there's no fault-tolerant quantum computers yet. So we for this particular work, we don't run any hardware calculations because the computers don't have enough qubits and coherence times. So this algorithm waits for quantum error corrected computers. And I don't know if there was something about software, but if there was, we use. Okay. We write our simulations because we need to sometimes simulate the circuits to make sure that they give the correct answers. We write this in CUDA-Q in partnership with NVIDIA. So it's a quantum CUDA language. But we also use traditional languages like Qiskit, and it's mostly Python-based, or there are Python interfaces. And we write, obviously, our own codes for that, but we use Python and libraries like Qiskit, Penylane, or CUDA-Q. So for that, we don't use any dedicated software. We develop our own to do the tests.
Thank you. All right. I don't see more questions on the chat, but maybe someone would like to unmute and ask. If so, feel free to raise your hand. Emil, are these works published somewhere?
Yes, it's on archive. So I can spread it or send it for those who are interested. It's been published in October last year, but now we updating the version because the paper was quite long, and we submit it to a journal now to await peer review.
Okay, good. So it's good that it's on archive already. All right. Yeah, last chance to ask question. someone is interested. So in the meanwhile, maybe I
Don't
was.
be afraid.
Yeah. Okay. Do we have some comments? No.
No.
Okay. Let me maybe just share my screen for one last time, just to announce the next meeting and also make some other announcements. So first of all, Emil, thanks once again for this great talk. And if anyone is interested and would like to stay in contact or just follow our activities, just to stay up to date, feel free to subscribe to our social media or join our Discord channel, follow our profiles, our YouTube channel as well. We would like to thank our partners once again for supporting us, Sonova R&D, Quantum.io, Onyx, Cogit, AQLab, FinQubit, and our honorary partners. If you are from Poland, you can donate 1.5% of your tax for statutory activities and support the organization of our events, not only the meetups, but also workshops and hackathons and other activities. And we would like to invite you to our next meetup, Warsaw Quantum Computing Group meetup on March 12th. Michał Parniak from the University of Warsaw will tell us about the Rydberg atoms between quantum sensing and quantum computing. So we'll start at 6 p.m. UTC+1 as today. So we hope to see you next time. And after this meeting, I will also send you a feedback form. And Emil, I will contact you regarding the recording later. So I will now stop recording and stop sharing.
Thanks, everyone. See you.
All right.